Hello everyone, welcome to Tux Riders and another episode of Applied Numerical Computing series. In this video, we want to have a deep look at the diffusion problem, or let's say parabolic partial differential equations and their numerical solution. So let's go for it. Okay, this will be a very detailed discussion. I don't want to go to the very depth of this, this kind of mathematical and numerical discussion. But yeah, I will describe the more interesting parts, and I'm sure that you will also enjoy it. That how we can deal with diffusion problems and the beauty of, let's say, numerical solutions that we can employ to solve these kind of equations. And for most of the projects that we want to describe in Tux Riders, they deal with kind of diffusion phenomena. So it is really important to know the characteristics and the behavior of these equations when we want to deal with them from the numerical computation perspective. So you know that diffusion means spreading in space and time, and it's a sort of parabolic PDE. So the equation will like this in one-dimensional way, but what we wanna discuss is an example of heat transfer and heat conduction. Let's say it can be applied to any other kind of engineering phenomenon that can be described using this equation, like mass transfer as well. But heat conduction is a very nice example. It comes from common sense, so you can easily imagine what the solution is all about. And this is the stability condition for the equation, as we discussed in previous video. This is very important. So the problem is for a graphite rod, so a one-dimensional rod that one end is 100 Celsius and the other one is 0, and we have it has a specific length, and we want to compute the profile of temperature inside it. And this is a problem that can be well described using the diffusion equation here. Okay, let's go for it. What we want to discuss in this video, in this episode, let's say in this session, is you really attack this problem from two perspectives. We can construct an implicit solution on it or an explicit one. And this is very crucial to know the difference between these two techniques. So let's start with an explicit implementation. In order to solve the equation, this is something that you know from the previous video. That is, you can simply compute, this is the forward difference in time. This is the time, and this is the next time step. This is the current time step, and this is the central difference for the second order of accuracy in space. But what you should pay attention is, you can see that what would I compute? This is when we rearrange it here. We want to compute the value of t at each point I in the next time step, assuming that we have the values of t in previous time steps. In order to spoil it, I can say that this is called the explicit approach. And if we have the other time steps also in the next time step, or let's say all in current time step except some in previous time step, this is called an implicit formulation. So these kind of things, when you know that this is a kind of explicit implementation, explicit formulation that has the benefit of easier implementation, easier programming, and coding in action, but it has its own certain limitations. Let's see how this explicit formulation works. It can be easily discretized using forward time and central in space, as we discussed in previous videos. So with a simple loop, we can compute it. And we apply also the boundary conditions. We know the values at two ends. That's why you see that it starts from 2 and it ends with -2. That's because we know the values at two ends of the road. This is the way that we can apply boundary conditions. And then, yeah, this is the solution, numerical solution, especially in the beginning, because we didn't have enough time steps. Let's see, what is the default value of nt is after 100 time steps. So this is not really enough. You can see that the diffusion, it starts from the beginning. It's like a step function that is 100 at this when it is x equals 0. But over time, eventually it starts to diffuse. But also for the boundary condition, this is worth to mention it here that we have different types of boundary conditions. For Dirichlet boundary conditions or Dirichlet boundary conditions, it means that you have the certain value, the specific values at the boundaries. Like in this case, this is 100 and 0. We know it, but at some points, so this is let's first see how it looks in action in when you solve it. So with 1,000 of data time points. When we continue the simulation enough, you can see that this is a sort of linear distribution of the temperature inside the road. But in some cases, you want to have Neumann boundary conditions. Like, just let's say that you want to say that, okay, at one side I have 100, let's say 100 degrees of Celsius, and the other side is a sort of insulation. That there is no flux, there is no heat flux. And how we can deal with this? This is a kind of Neumann boundary condition, because you know that the heat flux is the first derivative of temperature in respect to x, or respect to coordinate system. And this is the heat flux. And when you want to say that this is 0 or equal to something specific, that it has a constant heat flux or even a variable one, then this kind of formulation is called Neumann boundary condition. And so you need to discretize it. And then when you say that, yeah, this is actually, so this is a kind of discretization for this term, and this is equals to Q. And you can apply the same thing, the same principle on the equations when you implement them. So in this case, when you say that it is 0, it means that the values of t at the two last points are equal, are the same, let's say. So when we apply this kind of boundary conditions to our formulation, you see that at each time step, we apply the Neumann condition here. And then we have these results. Instead of from 100 to 0, this shows very nice visually that there is a sort of constant rate of temperature change here. And then for explicit schemes and boundary conditions, as we mentioned, this is a kind of stencil that we described in previous videos, how it's useful for understanding, visualizing the concepts of numerical computation. This is actually, it shows the interconnection of this of the points that we need to compute the values. So for example, it says that for each point here, like for this one, we need the value of the previous time step for the forward difference in time, and also 2 of this one and this one for the central difference in space. That's what it means actually. But if you do this, and if you implement this explicit scheme and try to really change for example, the time step, or let's say the delta x, the grid size, you see that it has some certain problems. Or you want to increase the rate of convergence by increasing the CFL value, the CFL number. It results in a big problem, like what you saw in the previous video when we discussed CFL. And if you noticed, now that I told you about the definition of explicit computing, explicit formulation, you see that all we discussed in previous videos, they were all explicit, and that's why they had certain problems in convergence. But then what implicit, what is implicit formulation? This is very, very cool. So again, for this kind of for the general diffusion equation, if we want to employ the implicit scheme, as I said, you use, this is actually for the forward difference in time. This is for this one. But for the central difference in space, we use the points at the current time step. So this yields to something like this. But then you may say that, yeah, this shouldn't make any difference in the formulation. But it does. Let me show you. When you formulate it in this way, you try to bring all the unknowns, let's say, like in this case, these are all the unknowns that we don't know the value of the current time step, n+1 for t. We bring them all to the left-hand side of the equation, and then for every, let's say for each space grid points, we can write it. By doing this, you may notice that you have different, each of the coordinate system, each of the values of t at certain locations, at certain grid points, are repeated in several equations. I mean that you have, for example, for tn+1, the current time step or next time step, you know that this is actually, if I call it this previous time step n, that n+1 means current time step. For the current time step at the location 2, let's say this is 0, this is 1, and this is 2, so this is 2, t2, it has appeared here, here, and here. This is really different from what we had in explicit formulation. That in explicit formulation, for example, this one had its own equation, and it didn't appear in any other equation. But in this case, it has appeared in 3 different equations actually. And if it is in 2D or 3D, it will appear in more equations. And as a result, we need to construct a kind of formulation for this, that writing all these equations and then trying to get an equation like ax equals b, the famous linear system of equations that you need to solve using a kind of solver or a kind of linear algebra system. This is the difference between implicit and explicit. Let's see how we can go for it. So in action, before going for that, one of the other prominent differences is for the boundary conditions. That in this case, because we are working with the current time step specs, especially for Neumann conditions, you need to formulate it like in the current time step and then the next time step, and they appear just on the right side of the equations for the nodes at the very end or the very beginning of for example, of the domain. In 2D or 3D, it's the same concept. By doing this, we have more equations for those nodes at the end, and we add the b which comes from the right hand side of the equation to the b that we get from the right hand side equations of the other nodes. And so when we write all of these things, we end up with such an equation. And then we need to employ a kind of solver, as we can see here. Let's go on. You can see that we need to employ a solver to solve the system, and then we will have the final solution of the problem. So in this case, this is the problem formulation. And then when we compute the left-hand side and the right-hand side vector, so the right-hand side is a vector, the left-hand side is a matrix, because we had the points, let's say, let me write it. When you say that this is the matrix, this is the vector of t that we want to solve equals a vector of b, and it contains also the boundary condition. But for example, when you have here t2 equals, for example, b2, you have still some elements here, here, and here. And this one, because you know the concepts of multiplying the matrix on a vector, this is where it is correspondent to this one. So when you have for the terms that we have two, you may have, for example, a term that is, let me call it A2 here, you may have it here also, and here as well on the fourth row, and then that's why you have T at different, that's the reason behind this is because you have T2 at different locations, different equations, as I stated a minute ago. And that's why you need, after computing this matrix A and B, you can easily solve AT equals B to solve for all the T's temperature at all the grid points that you have for each time step. And then you do the same thing. So you do the same thing at the next time step, and you go on. This is how the implicit formulation of problems work. And you can see it here that we compute the left-hand side operator or the matrix for all the points. This is quite simple. If you compare the code to the formulation, you will see that it is just what we discussed. And for the right hand side, this is the B. And for each time step, we compute these things. And then you see that this is what I said. For all the time step, T1, T2, it goes on. You compute B and you compute A. In this case, A doesn't change over time. This is, a sort of advanced case, but because the diffusion coefficient is constant, when you write this formula, you can see that the A matrix doesn't change eventually. So you can compute A only once. But in some cases, if you have, more advanced things, you will see later on in Tux Riders projects, that in some cases you will have a variable A as well. So you need to compute A at each time point. And that's why here the name of this function was operator, because you define it only once. And then at each time point, we use the linear algebra subsystem of SciPy. Sorry, you can go back to the SciPy video if you don't remember what that is, to solve this AB. So this is actually what it does. It computes the linear system of A, X equals B, and in this case, this X is actually the temperatures. So this is actually the T here. And then we apply the Neumann boundary conditions also here manually. Okay, so let's go on. And then we can plot a solution. You can see after, let's say, again, 1,000 of time steps, you can see that, this is exactly the same solution as the explicit solution that we obtained previously. And this is very, very nice. Very, very nice that the same problem, different formulations, they yield different approaches, let's say, they yield to the same result. But then the surprising thing is, this is as you remember, this is the CFL condition. That is actually, we had it always like it should be 0.5, and this is what we had for this implicit formulation. But surprisingly, this is very, very nice, because then you say that, this is very difficult. I just stick to the explicit formulation and that's all I need. But in reality, as you can see here, even with sigma 5, the CFL 5 times more than the one that we discussed in previous video, that it should always be less than 1. It is 5 times more. It is still stable. And this is the big advantage of implicit solvers, implicit formulation, that they are, I think it's mentioned here, that they are unconditionally stable. This is a very important term. What is also very important to mention here, when you say something is stable, it means that it never collapses, but it doesn't mean that this is very accurate. So accuracy is another thing, that you say that this is correct. It depends on lots of parameters, because it depends on the various, for example, the parameter formulation, if you have correctly modeled everything from the physical problem into your simulation, the boundary conditions, lots of things. The implicit formulation doesn't care about those aspects, but this is stable, unconditionally stable. So you don't really need to deal with, for example, the value of delta x and delta t in order to avoid divergence. But the correct choice of this delta x and delta t is very important. So you should still play with delta x and delta t in real world problems, as we will do in real projects that I want to show you on Tux Riders. But in theory, it always converge. So this is something that, at least from the implementation perspective and debugging perspective, sometimes can be very, very beneficial for you as the modeler. And this is actually the implicit scheme and explicit schemes. And then later on, there are also more notebooks here for applying the same concepts on 2D. For implicit, it will be a bit more complicated. For explicit, it is not actually. So because this is the same, you can see that this is the full conduction, 2D heat conduction problem that can be formulated into this one, a simpler one. And then the problem statement is like we have kind of insulation, as I said here. So this boundary and this one is insulation, so Neumann boundary condition, and this one are defined with Dirichlet boundary conditions. But the same formulation, when you follow this, you can see that this is very simple. But it's just from the implementation perspective, you need to deal with two-dimensional arrays for just storing even a single variable of space, like for x and y. They are still a space, so single variable, but you need to store them into two-dimensional arrays. And also sometimes, you need to deal with the order of stuff. So in programming, you have these kind of notations for order, let's say order of preference, but in reality in math it can be different. So this kind of stuff can be really a bit annoying in the beginning when you want to implement something like this. But generally you can see that the discretization scheme is very simple. So for this one, again, we have the forward difference in time, and the central difference for each coordinate, for each dimension, let's say. So this is for x dimension, this term, and this is for this one. But as you can see, this is a different index, with different index. So this one is with the I, current I, and the previous I, and this one is with J, because this is when you have, for example, point like this. This is ij, and when you're talking about, for example, this term to discretize this one, then you are dealing with I and j plus 1 and ij minus 1. So that's why for the central difference in y, you have to choose the correct index to change. And then, this is for explicit formulation, and bringing the only unknown, which is this one, to the left and the rest to the right, the easier implementation of the explicit scheme. And this is a really nice demonstration of what is happening. So the stencil will be 3D this time, and this is the next time step, this is the previous time step, or let's say current time step, previous one, and ti depends on the value of the previous time step. Here you can see on these grid points. Very nice. And then you put this in action, in the code, you implement it. And these are for the boundary conditions, for the Dirichlet condition, and also for this time you need to, for the Neumann condition, it should be really important for the index, pay attention to the index, and also the direction at which they are applied. So Qx and Qy, because we had two different boundaries that they were insulated. And for the stability, this is explicit, very important. And this time we have two dimensions, so they should be, it should be satisfied for two dimensions. So it's better to say that it's 1/4. And then for the code implementation, this is what I said for the storage. You should pay attention that sometimes the math and the programming is different. This happens a lot in programming of numerical computing solutions. So you need to store the solution in an appropriate way that you are aware of as the programmer. and then implementing it again, forward time, central space, and yeah, this is how it works. And then you discretize. You can have even different spacing in space for x and y. This is very normal to happen also in real world applications. And then we visualize the results, and this is very, very cool. As you can see, that the numerical solution works, because as you remember, we had like 2 Dirichlet conditions here. As you can see, they are always at 100 here, and then I'm not sure if it was a fixed let's say flux or no flux at these boundaries. I think this is no flux, and then this is it's just something that moves to this direction. The heat actually is exposed, and then it moves to this direction in a sort of semicircle pattern. Yeah, this is for the explicit formulation, and for the implicit one, I suggest that you go through this yourself, because I don't want to go to this. This is a bit more complex, but just from the implementation perspective, because I can show you, because the same problem, and then for the formulation, now you see that you have this unknown here, and everything is again according to the time index, according to what you see in the superscript here. They are all unknown, and this is, then now you know that this is a sort of implicit formulation. And for the implicit formulation, you need to define the matrix, again defining the way that you want to store the points in your matrix, in your arrays, in lists and kind of stuff. And then you choose the boundary conditions, you apply the boundary conditions, and also for the corners, bottom corner, top corner, still you need to adjust these things in the implicit formulation, and then you have the linear system that can be computed according to the values that we obtained from previous steps, and this is what we have in the implicit formulation. But let me go to the end, and you see that the implementation is a bit more, let's say, yeah, different conditional statements, but right hand side, and then we compute the solution, and you see that it is exactly the same as the explicit formulation. Yeah, I didn't discuss the exact, the precise, the details of this implicit solution, because yeah, it's really out of scope of the goals of this series, but yeah, this is very similar to the one-dimensional case. Yeah, this is what I wanted to discuss. I hope you enjoyed it. This is very exciting, how numerical computing can help to solve complex problems of diffusion. Later on, we will add reaction terms and also convection terms to these equations, and then it will be even more beautiful. Okay, so have fun with it, and see you in next videos.